Hello, my name is Troels Henriksen. I'm a PhD student at DIGO, and as part of the Hyperfit project, we have been developing this language called Futhark that is intended as a target for code generators. As a sub-part of our work, we had to do some shape analysis in order to write our code generator, and the technique we developed is what I'm going to present here. And this is work with my supervisor Cosmin Wancha and Martin Elsman. Okay, so shape analysis is a technique whereby you determine statically at compile time what the sizes of the arrays in the program are. Now, of course, we don't usually know the size of our input, so we can't find exact sizes. We have to make them symbolic sizes and relate the size of our intermediate results to the symbolic size of our inputs. Doing this allows us to optimize the way we allocate memory, the way we reuse memory. You can see the two arrays have the same shape, then they can live in the same spot in memory as long as they're not live at the same time. So it's sort of a shape analysis doesn't get you performance by itself, but it's sort of a necessity for many other kinds of low-level optimizations. It's also very useful for doing bounce checks optimization. If you want to use it, if you want to use shape inference as a building block for other optimization, you need some sort of structured way to represent your shapes. You can't just have it's not very practical to just have some random symbol table stuffed over to the side and log that around inside the compiler. So we went for an approach where whenever we have a variable binding, we want to annotate the type with the symbolic size of each dimension of the array. So for example here, the result of this map is a two-dimensional array of integers where the outer size is m and the inner size is n, where m and n are also just variables in the program. For example, you can see here in concat, where we concatenate C with itself. The result is an array where the inner size is the same, but the outer size is twice the size of the original outer size. So, this is just an ordinary variable, so that's being seen by the compiler as just another binding. So of course there are several ways to do this shape analysis. One way that is used in some languages is to really encode into the type system properly and have the programmer provide proofs and annotations about what the sizes of intermediate arrays are, and have the compiler check it for you. This is of course easier on the compiler, but it's more work for the programmer, especially if the shapes aren't really easy to describe, and it can be harder for the compiler to optimize it if it wants to verify that the optimizations have maintained the proofs of the original program and things like that. Another approach, which is the one we have taken, is to let the programmer just write code without worrying too much about shapes, and have the compiler insert all the annotations for him. This requires a compiler to do more work and to be able to optimize these shape computations well. And of course, the programmer can have a hard time knowing whether the compiler does a good job of it. But for Futhark, which is supposed to be the target for DSLs, for example, we don't really want the DSL implementer to have to worry too much about this kind of low-level optimization. We just want to make it easy to generate some Futhark code, and then hopefully the Futhark compiler can do a good job with it. Okay, so a little bit about the Futhark language. It's not an interesting language by itself. It's just a vehicle for doing optimizations mostly. It's purely functional. It's not very powerful. We don't have user-defined higher-order functions. We have nested parallelism through some built-in higher-order functions: map, reduce, scan, and filter. We don't have arrays of tuples. We have tuples of arrays, which is a pretty standard thing to do. And all of our arrays are regular. So you cannot have a matrix where each row has a different size. They all have to be the same size. And our goal is to get this to run efficiently on GPUs. We're not quite there yet.
Can arrays be nested?
Sorry?
Can arrays be nested?
Nested, how you can have multidimensional arrays?
Of arrays.
Yeah, well, you can have multidimensional arrays, but you can't sort of box arrays. Okay, so this is what it looks like. We have a function f that takes some two-dimensional array of reals, and maps across the rows of that array and does a reduction on the rows, and here returns tuple. Our syntax for tuples is written with braces, so we can have singleton tuples. That's just a technical detail that doesn't matter much. And because this map function returns a tuple, the result of the map is two arrays, because again we have tuples of arrays, not arrays of tuples, so it has to do that. And then the two arrays are concatenated and returned. And this the main function just maps that f across the three-dimensional input array. So that's what it looks like. And we want to be able to optimize the shapes in this, be able to analyze the shapes, and make sure that our shape analysis results in code that can be efficiently computed to a GPU kernel. So our basic idea is to annotate the user-written program so that not only does it return the values, that is the arrays, but it also returns explicitly the sizes of those arrays. And then take this annotated code and split it apart into two chunks of code, one that just returns the shapes and one that just returns the values, whenever that is possible without duplicating too much code. And then we use and because all of these annotations are still written in the same language, we can use our general optimization and our entire compiler repertoire to optimize these chunks, these slices we call them. So for example, if you have a function from a two-dimensional array of ints to a one-dimensional array of reals, to a one-dimensional array of reals, we sort of add some existential context where we say, okay, for all sizes n and m, this array can be whatever size, and it returns some size s and an array of size s. That's sort of a type theoretical way of looking at it. In practice, we have in practice we have the function looks like this in Futhark syntax, and after the annotation has been added, it looks like this. So it explicitly returns a new integer, and this question mark 0 refers to the first part of the first element in the context. So this may be a bit confusing. Internally, it looks more like this, but for the serial syntax, we decide to write it like this. And the input sizes are also passed explicitly as parameters. That also means that all of the calls to this function have to be updated to explicitly take out the sizes and pass in the sizes of the parameters. And that would be down here if it was cut off. Another issue is with maps, because we only have regular arrays. So if you map with some function, you need to make sure that for every iteration of the map, that function returns the same size. And we could do the same thing as we did with regular functions, where we just make it return the size as part of the map function. But the problem is that then you get back an array of sizes, and what do you put for this annotation? I mean, you need to refer to any element of this array as long as they are all the same. But we also need to check explicitly that they are all the same. And so this doesn't really work. What we do is that we explicitly execute the first iteration of the map. We just inline it just before the map, like this, and compute the size of the first iteration. And then we modify the map to explicitly assert for every subsequent iteration that the actual size is the desired size. And of course, we have to insert a branch to make sure that the array isn't empty, because NS might be an empty array. And this is of course pretty slow to have an assertion inside of your map, but that's one of the things you have to optimize later on. So let's look at the same Futhark program I showed you earlier. It looks like this, and let's add some shape annotations. Now it looks like this. So you can see this function now explicitly returns the size of R, and we have inlined the first iteration of map, and we have the assertion down here. And this is sort of what the compiler does naively, and then it tries to optimize it. So the first thing we want to do is we want to take this function and try to split it into two functions, one that just computes the size of the result, and one that computes the actual result. That's what we call slicing. So the shape slice is just n plus n. What we really do is that we just take this function and we remove this r, and then we just do dead code elimination and see what it returns, and we look at whether that is efficient. So that's pretty. That just reuses our general simplification engine in the compiler. and we get back this trivial function. And for the value slice, we pass in the result of the shape slice as a new argument, and use that to annotate every place that where we originally computed the result size. So we have this res here now, and where it's used, we first call fshape and get back the result size, and then we call the value slice and pass in this s again. So every call to the original f function becomes a call to these two new functions. This also means that this inline first iteration, which only used the size, now only calls the shape slice, because otherwise it was just dead code by now. Okay, this is still not very nice, because we're still computing a size in here inside of the map, which means that we cannot allocate memory for the result of the map in advance, because we don't know what size it is. So we really want to take these shape computations out of the map. So we do a loop fission and do a map in advance where we just compute all of the sizes that are going to be computed inside of the map. Then, of course, because they are result sizes, we need to check that they are all the same. So we just check whether these sizes are the same as the size for the first iteration, and then we just reduce them all together with and assert that this is indeed the case. So now the assertion is outside of the map. And this syntax, this square bracket, angle bracket C, just means this assertion has to be run before this code makes any sense. It's just a way to prevent the dead code eliminator from removing the assertion, because it otherwise doesn't have any observable effect. So after this is done, we just use our standard optimizations. This is some map reduce fusion could happen here, for example. First, what we do is we inline fshape, because it's a very small function. So that just turns into n plus n. Now we can see here this map, we don't actually use a here. So we can turn this map into a replicate, and we can fuse this replicate with this map. And again, this map doesn't use I, so we can turn that into a replicate. And now we have a replicate that is going into a reduce. And I'll simplify. I can see that this is pretty much just this is the same as just doing a single AND with a branch. So it ends up looking like this. And actually, if our optimizer was a little bit smarter, it would be able to combine these two branches and completely remove the assertion. But that will have to be future work. But the end result here is that we have a map which with no assertion inside of it and no unknown sizes. All of the sizes are computed in advance, so we can do the allocation completely before this map, and which implies that assuming that f value is a nice function, we could put this on a GPU. All right, so for some operations like filter, you cannot compute the size in advance efficiently, because computing the size of the filter result is pretty much the same work as computing the filter result in the first case. So in that case we cannot do the slicing. But we still have some knowledge. For example, we know that the result size of a filter is never greater than the input size of the filter. And we should represent this in some way, because you can still use that to optimize allocation. You can just be conservative and allocate as much as it could possibly need. And if you do assertions that two arrays have the same size, that should also somehow be useful you could use that to make the annotation more precise and do some backpropagation. And finally, we need to actually use this shape information to optimize our memory allocation. We don't do that yet. Let's show you a quick example of how that could be useful. We have this program here. Let's try to add some shape annotations to it. Now we have the problem here that we compute a size inside of the map that is actually that is not necessarily invariant with x to x. So maybe we cannot. Maybe this n is different for each iteration of the map, which means we have sort of an irregular pattern. We don't have any arrays that are actually irregular, but they sort of appear implicitly when this program runs. And that's not very nice. So what we would like to do is something like doing the fission to compute to move the shape computation outside of the map, like this. This is the same thing as we did in another example. And then we can compute the total space requirements of the map in advance just by summing up all of these sizes And doing this allocation, this isn't implemented yet. This is sort of what we hope to do in the future. So we have some sort of allocation primitive that gives us back a memory block, and we can say that, oh, now this variable A is backed by this memory block at index I, where I is the result of a prefix scan on all the sizes. So this is a way for us to compute the memory requirements of this map in advance, and even though these variables may not have the same size throughout the loop. But this is future work. We haven't done this yet, but this is sort of the motivation for doing our shape analysis. Right. So, in practice, we've tried this out on some benchmarks on real-world financial programs. We have translated to Futhark, and the overhead of the shape analysis is very low. It's a constant, in fact. And this idea of reusing the same representation at multiple stages of the compiler has really paid off. It allows us to reuse the Fusion module for pretty much, or even for optimizing low-level things like shape annotations. And it seems like this our approach of generating explicit code and just trying to optimize as much as possible and leaving whatever we can't optimize for the runtime seems to work all right. Although we still don't have a good parallel code generator, so time will tell whether this really works in practice. So that's pretty much it.
Thank you. Questions?
Computation on shapes of values is a pretty standard exercise in dependent types.
Yes.
Why had you have to design a separate language instead of just embedding one in the dependent design language?
This is not the only thing we do. We didn't want to do dependent types because we want to use this as a target for a code generator. Well, the original language may not be dependently typed, and generating dependently typed code from a non-dependently typed original program just seems very complicated.
But your embedded language doesn't have to be dependently typed, even though if it's embedded in a dependently typed language.
Right, but we don't want to embed things in an independently typed language. We want to have to give. So our eventual audience are things like financiers who want to have DSLs for expressing contracts, which probably shouldn't be dependently typed.
Just one more question and then I'm done. Another type theory technique for estimating how much memory a function takes is linear types. Have you thought about having a linearly type?
We actually do. So we have something that resembles linear type. We have a uniqueness type system actually, although that wasn't the focus here. We have considered it, but again, it puts too much of a burden on whatever generates the Futhark code. But it's definitely something I would like to use to constrain it. So if you want to, you should be able to add some constraints, and the compiler should be able to. It's just more information for the compiler, so it should work.
Thank you.
What's your question?
So how does your solution compare to things like LMS? If you look at this project, this is a lightweight modular staging. It's kind of the idea is that you can stage any part of your computation and then move on to the next stage in your code, and then use the information you gain there. One example would be to compute sizes of arrays in advance. It's a more general approach, I think. You can build multiple stages and then generate some code for some intermediate language in the end.
I don't know LMS. So is this a user visible thing, or is it a compiler implementation technique?
Well, it's kind of, I think it's, the idea is that you implement DSLs using this LMS, and there's an example, something called Delight, which implements also parallel operations like map, reduce, and filter.
Yeah, okay. I don't know it, but so yeah, the delta is in the details. But our basic technique is that we want to expose something rather simple to the user, and then try to do as much magic as possible. Well, not magic. Try to do optimize as aggressively as possible without the user having to know too much about what's going on.
You mentioned loop fishing a few times.
Yes.
So whether under what conditions is it safe to do so? Whether under the context of your language.
Oh, it's always safe to do because the language is pure. It may not always be efficient. We wrote a paper for last year's FHPC about our fusion algorithm. So we do produce a consumer fusion, and that's it. But we do fuse things like filter into reduce, and it's all right fusion algorithm, but it's greedy, so sometimes it does things that are not so good.
There may be data dependencies. So
Uh,
you may depend on the input value in input or output array or whatever. I'm not sure that always safe.
yeah, well, data. Yeah, well, it's produced consumer fusion, so you only fuse when there's a data dependency.
I think
Fission.
Fission. Yeah. Okay. So fission is done. Fission is only done in a very few special cases, like for splitting out the sizes. And it's based on just duplicating as much code as necessary, then trying to remove the duplication and seeing whether the result is fast enough.
So do you have any proof that's safe?
No, I mean it seems obviously safe because, well, it's a pure language, so you can't really. When you have something is bound, it's never going to change. So if you just duplicate the binding, then you can't observe intermediate stages of the computation.
Yeah, you mentioned that you have these higher order operators like map, forward, filter,
Yes.
and scan. Do you also have a map too, actually? And if so, I mean, to perform something like addition of arrays and
Addition of array. So the thing is, inside of a map you can have whatever you want. You could have another map inside of the map. That's one of the things in Futhark. It doesn't constrain what you do inside of your anonymous functions. So you can do, if you want to do nested parallelism, you just have a map where the function does another map. So we don't need a specialized map to.
Do you have an optimization for that, or would you execute it like this?
So as I said, we don't have an efficient code generator yet, but we expect to do flattening at a late stage in the compilation.
Also, map take any number takes any number of.
Oh yes, yes. So we don't have these arrays of tuples, but you can pass however many arrays you want to all of the maps and reduce and things like that.
Okay, that's map 2.
Okay.
and
Okay. I thought you meant
Yeah.
What's the
multi-dimensional.
result shape then?
That depends on what the function returns. So, for example, let's see if I have an example somewhere. This case, for example, this is a map where the function returns two values. So the result is just two arrays, where the element type of the array is just whatever is here. So if that was an array of reals, this would be a two-dimensional array of reals.
Those are the results, or
This is the result type, yes.
if you have 2 arguments?
Then there would be more arguments here.
And
The number of arguments does not have to coincide with the number of results.
just questioning if the arrays A and B have different sizes.
Yeah, then that's an error. That's checked by an assertion before the map.
Okay.
So we also have a complicated assertion optimization, which was presented at Array this summer, which tries to optimize away all of the assertions.
Okay, any more questions? That's not the case, then I think we can ask Holz once again.